Okay, so there's one last thing we must talk about. That is, we have claimed that a binomial queue of n elements can be built by n successive insertions in a linear time in big O of n time, and therefore the average complexity for each insertion is supposed to be a constant, right? Now let's try to prove it. Well, before we do, the question is the worst case. What is the worst case time for each insertion? So what is the worst case? The worst case is when all the trees are full and we make one more insertion, right? Then we have to make links all the way through, right? So it's going to be log n. So in the worst case, one insertion still takes log n time. But what we are trying to prove is that the amortized time for each insertion is supposed to be a constant. And to do amortized analysis, we have studied 3 different methods, right? And so let's try to prove it with different methods so we can get a clearer picture. First, let's try the simplest method. It's the aggregate method. Do you still remember what that is? Aggregate means we simply add up all the steps and count the total number of steps, right? And then divide the total sum by n to obtain the average, right? Now let's count the number of steps. When we insert the first node, we obtain b sub 0, one tree, and it takes only one step to create a new node, right? When the next one comes in, we're supposed to create a new node and make one link, and therefore to remove b sub 0 and obtain b sub 1. But there's still one tree only with b sub 0 being empty, right? It takes 2 steps. All right, and when the third node comes in, it will be the simple case again. It takes only one step to create one node. All right, now here comes another bad case. When the fourth one comes in, we obtain b sub 2 by creating one node and making 2 links, right? And if that's not clear enough to see the pattern, let's try to insert more nodes. Next one is going to be a good case, right? And one step plus one link, and then one step, and then one step plus 3 links, right? Link, 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 and to get B3. And then we're back to the best case again, and so on and so forth. Can you find the pattern? After n steps, what's going to happen? Well, first of all, how many steps do we need in total? If there are n elements to be inserted, the total number of steps is, of course, n, right? The difference is made by the total number of links. Can you find any pattern here? Say we can have this link 1 in every 4 steps. If it's not clear enough, you can try to insert more elements and see, right? We have one link here, then after 1, 2, 3, 4, we're going to have another link 1. And 1, 2, 3, 4, the next one is going to be another link 1, right? So we have one link in every 4 steps. We're going to have 2 links in every 8 steps. We're going to have 3 links in every 16 steps, and so on and so forth. So here is the pattern. Okay, so n is the common numerator, so we take it out. And then we have 1 link for every 4 steps, 2 links for every 8 steps, 3 links for every 16 steps, and so on and so forth. And I assume that you have all studied calculus, so you know that when n tends to infinity, this is an infinite series, but this series is a convergent series, which means it's bounded above by a constant. So some constant times n is big O of n. So put them all together, the total time taken would be big O of n. And we're done with the proof. That's a very simple way, a straightforward way of proving the conclusion. Just to have some fun, as a kind of exercise, let's try to look at this problem from another point of view. You see that when we encounter those step 1 cases, we can consider ourselves as in good luck, right? So while we're in good luck, we like to save some of our good luck in a savings account. All right. So for example, if we are lucky, we like to save $1 as a credit into our savings account. And when we encounter links, we consider ourselves in bad luck. Okay. For every bad luck, we like to withdraw $1 from the account. And therefore, if there's one good luck plus one bad luck, they just canceled out. It's like saving $1 and then withdraw $1. So nothing is increased. Okay. Now here we encounter another good luck. So plus 1. So here we have plus 1 minus 2, and therefore this is going to be minus 1. And so on and so forth. So this one we plus 1 and blah blah blah. Here we have plus 1 minus 3, and therefore we get minus 2. And when we sum them up, it's a kind of what? It's the method of what? It's the accounting method, right? But the puzzle is, why do we define it to be positive 1? If we encounter a good luck, why do we only save $1 here? Why not $2? Why not $3? Is it a random number? Certainly not. There must be a reason behind, right? Let's observe one thing here. Expensive insertions remove trees, while cheap ones create trees. When we encounter a bad luck, we make several links, but every time we make one link, we are actually removing one tree from the forest, and therefore give more spaces to the next insertion. So the next case will be the best case, right? Then let's check out the change of the number of trees after each insertion, right? At the very beginning, we have an empty queue, and therefore the number of trees is 0. And after this step 1, we created a new tree, and therefore the number of trees is incremented by 1. That's 1. Okay? And after the second insertion, there's still just one tree, so there's no increase. So that's 0. Okay? After the third step, we have 2 trees. So we have 1 increment of the number of trees, right? So for example here, before the insertion, we have 3 trees. After the insertion, we have only 1 tree, and therefore the net increase of the number of trees is negative 2. So it's a good way to define the potential function. So let's try to prove by the potential method. Okay, and by observation, we realize that an insertion that costs C units results in a net increase of 2 minus C trees in the forest. Is it really so? Let's turn back to check. Okay, so for example, if it takes 3 steps to complete insertion, then it will cause a net increase of 2 minus 3. 2 minus 3, that's negative 1. So 1 less tree than before. Okay, if it takes only 1 step to do the insertion, the net increase will be 2 minus 1. That's 1. 1 more tree is created. Okay, and so on and so forth. If the total step is 4, then the net increase will be 2 minus 4, that's negative 2. If we take this one as a fact, then it's going to be simple to design the potential function. So let's denote the cost of the ith insertion to be C sub I. That's the actual cost. Okay, and we define the potential function to be the number of trees. The number of trees after the ith insertion. So at the very beginning, it is 0. And then starting from the first insertion, this number of trees is always positive, and therefore it means that this potential function assumes its minimum at the very beginning, so it's fine. Alright, and according to this observation, we see that what is the net increase of trees? This is before, this is after, and this difference gives the net increase of the number of trees after the ith insertion. Okay, and this increase is supposed to be 2 minus the actual cost. And we move the actual cost to the left-hand side of the equation, and here we go. Now let's sum them up. And what do we get? Here we have the total sum of the costs plus all those potential function values in between are going to be cancelled out. So eventually we're going to only have the first one and the last one remained, right? It doesn't matter what this one is. We just know that it's a positive number. That's good enough. Okay, so the actual cost plus some positive number must be equal to, when we sum up for n terms, this is going to be 2n. Alright, so we have that this is 2n minus some positive constant, n is bounded above by 2n, and therefore it's big O of n. And that finishes the proof. So our conclusion is that although for each insertion the worst case complexity can be as bad as log n, but its amortized bound is a constant. It's just 2. Okay, and so much for today. So in this week, you're supposed to have your first research project about shortest path algorithms with different kinds of heaps. Okay, and there's a contest hosted by this DIMAX, means the Center for Discrete Mathematics and Theoretical Computer Science. Okay, and they have the nice implementation challenge on the subject of shortest paths. Okay, and so this project requires you to implement Dijkstra's algorithm. Do you still remember what Dijkstra's algorithm is? Well, you'd better answer yes, right? Okay, you're supposed to implement Dijkstra's algorithm based on the mean priority queue. Well, Dijkstra's algorithm is a typical greedy algorithm, right? We're supposed to find the shortest distance between two vertices, and by collecting those vertices one by one into the solution set. And being greedy means every time we're gonna collect the one with the smallest distance, right? It means that we can maintain all the distances in the mean priority queue, in the mean heap. So every time we just call delete mean, so to obtain the new vertex with the smallest distance, right? And so far we have studied ordinary mean heaps, and we also studied leftist heaps, skew heaps, binomial queues, and there's one more, Fibonacci heap. It's another form of priority queue. Okay, and the goal of this project is to find the best data structure for Dijkstra's algorithm. So you're supposed to compare at least 2 different heap structures, and Fibonacci heap must be one of them. Alright, and if you decide to try this one, you can visit the website of this organization, and you can also download the USA road networks for evaluation. Okay, have fun.